All right, chemistry students. Today we're going to look at some notes on limiting reactant, excess reactant, and theoretical yield notes within the context of stoichiometry. Now, when you see one of these problems, typically the giveaway will be how many givens are written in the initial problem itself. So you'll often notice that these are a little bit different than some of the easier mole conversion ones you would have already done. If I look at this first problem here, it says 5.37 moles of solid sodium reacts with 20.9 grams of aqueous aluminum nitrate. Right away, I notice that there's two initial numbers that I'm given. So when I do the math for a problem like this, I'm going to have to end up solving both of those given numbers as separate stoichiometry conversions. Now, it gives me the skeleton equation, but it's not balanced. So the first thing I need to do before I do any stoichiometry calculations is always balance that chemical equation. If I look at this equation, I've got one Na on both sides, I've got one aluminum on both sides, but on that left side I have three of those nitrates. The right side only has one. So I would need a coefficient of a 3 in front of my NaNO3, which changes my sodiums to 3, so then I need a 3 on the left side. Now, any blank we assume stays a 1, right? So we just keep those exactly as they are. Now, part A says determine the theoretical yield of aluminum in grams. So we're solving for a final answer of the mass of aluminum. So in this case, I'm going to write down both of my givens. The first one, 5.37 moles of sodium, Na, over 1. I'm actually going to bump this down a little bit so I have some more room to write. My second one, I'm going to write down 20.9 grams of an aluminum nitrate over 1. Now, I'm going to solve these separately. Both of these are going to be conversions where I'm trying to get to that grams of aluminum at the end. My first step in my first conversion here, I'm already in moles. I want to just straight convert from moles of Na into moles of aluminum. Now remember, this step is called the mole ratio, and we get those numbers from the coefficients in the balanced equation. My balanced equation, the coefficient for aluminum is just a 1. So it's a 1, and then my coefficient for sodium is a 3. So it's a 1 over 3 ratio. This allows me to cancel out the units, moles of sodium. Now, I'm in moles of aluminum now, and the answer is asking me for grams of aluminum. So I would need to do one final step where I cancel moles of aluminum, and I use my periodic table to look up the molar mass of aluminum, which is 26.98 grams for every 1 mole. Now this would allow me then to cancel out moles of aluminum, and I would get into mass of aluminum at the end. So I'm going to pull up my calculator here. All right, 5.37, 5.37 divided by 3 times 26.98 gives me a total final answer of 48.2942. If I look at my givens here, my initial number started with 5.37. That started off with 3 sig figs. So my final answer is also going to need to be rounded to 3 sig figs. So I'm just going to straight up round this answer to 48.3. So that way I don't have to do any extra work here at the end. 48.3 grams of aluminum. Now, I'm not going to circle that answer. I'm not done yet. I need to do my second calculation here, where I'm given grams of aluminum nitrate, and I'm also going to solve for grams of aluminum. Now, this one's going to be a little bit more work because I first need to get that mass into moles of aluminum nitrate. So in my calculator here, I'm going to have to add up the mass of 1 aluminum, 3 nitrogens, and 9 oxygens. So I'm going to take 26.98 plus 3 times 14.01 plus 9 times 16 gives me a total molar mass of 213.01 grams. 0.01 grams of aluminum nitrate. Cool. That allows me then to cross off grams of aluminum nitrate. Now I'm in moles. Now it's going to be just like the problem above, where I'm going to cancel moles of aluminum nitrate, convert straight into moles of aluminum. Again, this is my mole ratio, so I'm looking for the coefficients in the balanced equation. So I look at each of those coefficients. In this case, they're both 1 over 1. That makes it easy. And then my last step is actually going to be the same as the one above, where I'm going to convert moles of aluminum into grams, 26.98 grams of aluminum. Now, in this case, this problem also started with three significant figures. So I'm going to round my answer to be the same as it was before. 20.9 divided by 213.01 times 1 divided by 1, don't need to write that, times 26.98 gives me an answer of 2.647, which I'm going to round to 2.65 grams. 2.65 grams of aluminum. Now, when I get to the end of a problem like this, I have two final answers. The theoretical yield, so this is what it was asking me to solve for, the theoretical yield, right? The theoretical yield is always going to be the smaller of the two. So I'm going to make a note to that over on the side here. The theoretical yield will always be the smaller final answer. And this gets down to the idea of limiting and excess reactants. When we do a reaction, ideally we're reacting everything perfectly, where all of our reactants are reacting 100%. But in reality, it doesn't always work that way. Typically, you have too much of one thing and you run out of the other, right? They're not going to run out at the same time as each other. So in this case, what this represents is the smaller answer represents how much you can make of whatever the least reactant you have, whatever one's going to run out first. So I'm going to circle the 2.65 grams, and I'm going to label this my theoretical yield. Theoretical yield. And then the way that you figure out the limiting reactant is whichever reactant got you to that theoretical yield. So my limiting reactant is going to be the aluminum nitrate. That's the one that's going to run out first. And now by process of elimination, I know that the other one, in this case the sodium, that's going to be my excess reactant. That's the one that I still have left over at the end. The limiting reactant, by definition, 100% of it reacts, which means I have none remaining. All of it is gone. If I were to look at this reaction at the end, and I want to say, oh, how much extra aluminum nitrate is there? There's none. That's it. It's all gone. If I want to solve for how much excess reactant of the sodium there is, I could do another calculation and solve for that, which is going to be something that we do in a future note page. But this is just kind of identifying the basics here. So the limiting reactant is the one that gets used up, and it's the answer or the given that gives you the smaller final answer at the end. That's the theoretical yield. The excess reactant is the one that's going to be left over. That would give you a larger yield at the end. All right, try the next one on your own, and thanks for tuning in.